Good morning, class. This is Mr. Roberts at Shasta High School, and we are in section 4.1.2 today. We're continuing our talk about uh, lines of fit, the scatter plots, the equation of a line that attempts to fit the data, and today we're going to be adding a new term, residuals. I do label this as section 4.1.1. 4.1.2 rather, I'm sorry, 4.1.2. And I want us to start with this. This is a problem from yesterday's Delta Math assignment. And when I looked through your work, this was something that I could see that many of you were struggling with. So I want you to get this example in. We'll see these problems come back again. And I did add an extension. You can continue to work on the Delta Math assignment for a new late date, and I think it's only taking off 5 percentage points, so you can still get 95% on it. So let's take a look at this. As I look across, an important idea to keep coming back to is how many terms do I see? Big picture, looking across this, I only see these two subtraction symbols. And I know you're saying, but Mr. Roberts, what about the ones that are up in the fractions, right? Those are part of that fraction thing, right? So when I see this entire thing right here, that's a single term. Yes, it's true. The numerator has two terms in it, but that is just one entity in and of itself, right? So it's 2x minus 5 over 14. I only see the two subtraction symbols, and that breaks us up into 1, 2, 3 terms on the left hand side and just a single term on the right hand side. Now I point that out because we're going to use fraction busters to get rid of the fractions. So I'm going to multiply through the entire thing, both sides, by 2 times 7. And I'm just looking at the 14 and the 2 that are my denominators for the two fractions that I do have. And I'm saying to myself, hey, if I multiply this first fraction, this one with the 2, if I multiply that by 2 times 7, definitely the 2 will be eliminated, right? So it's going to be gone. Now, the reason why I throw the 7 in is the next fraction over. If I multiplied that by just 2, I'd still have 1/7 as a fraction. So I'm bringing along this 7 for the ride also because that is going to destroy the second fraction as well. So 2 times 7 or 14 will completely get rid of all the fractions. So I'll leave the green things there. So I'm intentionally going through now and I'm multiplying everything by 2 times 7. So I've got a 2 times 7 times the 2x that I saw. 2 times 7 times 2x. And the next thing I've got is this subtraction problem. I'm just going to probably write this as a -1, right, times the 2 times 7. Again, that -1 just got its 2 times 7. Then I've got this -3. Now I need to multiply this third term on the left-hand side by 2 times 7. That numerator is complex. The numerator has two terms in it. It has a 3x plus 3. So what I'm going to do is I'm going to multiply the numerator times 2 times 7, but I've got to be careful because I have to multiply the entire numerator by that. So I've got 2 times 7 and then times the 3x plus 3. That vinculum is a grouping symbol, that long fraction bar. It divides the fraction into the top and bottom. And I really need to know what the 3x plus 3 is before I divide by the 2. And then below that I've got another 2. And then on the other side of the equal symbol, we've got the 2 times 7, and then I've got the 2x minus 5. Now if I'm being honest, this is not a step I consistently show. I just want you to visually see that every single term got new factors of 2 times 7. It's really important. My claim is that I'm multiplying each term by 2 times 7. I'm pushing across these factors of 2 times 7. If I don't do that, that's a problem. But because I did it, if you have equal things and you multiply by equal things, you get equal things, right? So this is now an equivalent equation. It says the same thing. It has all the same solutions as the equation above it. What I get from that is that this is now, 2 times 7 times 2, this is now 14 times, this is 28x minus the number 14. That's 2 times 7 times a -1. And then here's the cool thing, right? This fraction, this 2 over the 2, that's gone, right? So what I end up with is just a 7 times 3x plus 3, and I can distribute that 7 across, so it's going to become a 21x. Got to be careful here because this is a subtraction problem. So I'm gonna put parentheses around this. Is going to be 21x plus 21. The reason why that's important is because I need to make sure I'm getting the opposite of both of those, right? So I've got minus the 21x plus 21. And then on the other side, this is going to equal, well, the 2 times 7, right, is 14 over 14. That is 1. So I'm just left with the just the 2x minus 5. 2x minus 5. So all of a sudden I no longer have any fractions. It's a lot cleaner to look at. So I'm just going to solve this thing. I do want to rewrite it one more time without these parentheses. So this is going to be 28x minus 14 minus 21x minus 21 equals 2x minus 5. Over on the left hand side I've got the 28x minus 21x, which looks like just 7x. And then negative 14 and negative 21 looks like a negative 35. And then on the other side there's a 2x and a negative 5. I'll take away 2x from both sides. And then I'm going to add 35 to both sides. And then I'm going to divide both sides by 5. So x is the number 6. I could plug that into the original equation with the fractions, or I could plug it into this revised form. You're better off going all the way to the beginning, but x is 6 is our solution. On Monday when we were looking at Tinker Toy Tech, the idea was that we had some data that my students had collected a couple of years ago. And I think probably I should have used a better distribution of the data because there were probably a lot more points scattered out in these areas that kind of would have filled this in better. As this is, if I was to describe the shape here, this looks like it's slightly curved, doesn't it? It looks like it's curving up somehow. And I don't think that was necessarily the case with the original data set. So bad data custody on my part. But if I look at this student selected a couple of points and generated a line of best fit based on those points. And this line of best fit, the equation is y equals 3 over 40 times x plus 1. That's the model. That's the model that makes predictions about what happens with these numbers. And you can see if I take a number like right here, this is 105. If x is 105, right, the model is going to predict the number 7. You can see right here, here's, no, it's going to predict the number 9. Well, I didn't need to erase that. In between the 8 and the 10 is the number 9. So if I put in 105, it looks like the model is saying I'm going to get an answer of 9. And actually, when I plug that number into the equation, what it actually gives me, when I put in 105, it actually gives me an answer of if x is 105, y would equal 8.875. So it's close to 9, right? But it's not 9. So here's the thing. My model is making this prediction, right? It's saying y should be something, right? But if you look at my data set, you can see, well, that's not what your data set said. There's a discrepancy between my observed information, right? I have two observations here. One of the observations is that if I put in x is 105, I should get a number larger than 14. And in the other case, when I put in x is 105, I should get a number that's, somewhere in between 10 and 12. So we have a name for this discrepancy. A name for this thing that's a difference between what I'm observing and what the model says. And the name is the residual. Let's write that down. Residual. And we'll define that in just a moment. But we'll define it more specifically in just a moment. But right now, just visually, let me show you for this point right here, this point has a residual. And the residual is simply the length of this line segment, right? It's the length of the line segment between what was predicted and what was observed. And in fact, this residual is actually positive because it sits above the line. It's a positive residual because it sits above the line. So let's take a moment and define what residual is. So the residual is this difference between an actual value and a value the model predicted. So let's come up here and we'll write this down. In fact, I want this to live in your notes. So I'm going to pause here for a moment, but I'll read through it with you. So it says a residual, the residual is equal the actual value. That's the value from the data set, what you observed when you were collecting data, the real thing, right? Minus the predicted value. And that's the value that we see from our model. So if I put in an x value into the equation we got, right, it tells me back what the model is predicting. Like in that down below here, when I put in 105 into the equation, it makes the prediction that y should be 8.875. So that's the predicted value. And then this value right here, right, the value, the y value, here's that point has an x and a y. The y value from our observed data point, that's the actual. So the residual is the difference between those two. So residual equals actual minus predicted. I've written wrap here, R equals A minus P. And again, make sure you jot down in your notes what I mean by actual. What do I mean by actual? And then what do we mean by the predicted value? So that's essentially what a residual is. And every single data point in a data set will have its own residual, right? I can go through and I can look at all of these points, and every single one of them has a residual, right? Well, I could say all of them, but then I find a point like, actually, there's not a lot of them that are right on, but if you look at this data point, right, that data point is pretty much on the line. So it's like that data point has a residual of 0 or very close to 0. I think I know because the y-intercept of our model, the y-intercept of the model was +1. So I know that this data point right here has no residual. So points that live on your line, see this one looks like it has a very slight residual. Data points that live on your line do not have residuals, but every other data point, right, the residual is the difference between what's the model predicting and what I'm observing. So it's the differences, it's the length of these line segments, right? The lengths of those lines are the residuals for each of the data points. And it's just making the common sense observation that when we build a mathematical model, right, the model is not going to give us perfect answers all the time. We're attempting to model a situation, and there could be, confounding variables. There could be other things that are lurking variables that we don't have a perfect picture of reality. But based on the model we built, we're making quite a few assumptions. But based on that model, we're getting pretty good data, particularly in the range, right? Particularly in the range that our data is. So from 0. To me, this model looks decent from 0 to about 95. If I get much further outside of that, even this model looks bad because the shape of it looks like it's skewing upwards. Okay, so that's the big idea. What are we looking at today? We're looking at residual. What is residual? It's the difference between an actual value and the predicted value. So not required for your notes, but I want you to, there's something else that's coming up in a minute, but I want you to kind of know the background here. You can look at the problem in the textbook. This is in section 412. But essentially, packaging, right? Packaging needs two things, right? There's the square inches in this case that are required to build a box, but then also there's the volume of what's inside the box. And you can design packaging so that it minimizes the use of cardboard. It makes the cardboards smaller, right? The amount of it, but it maximizes the volume. So using less cardboard material, you can put more product inside of it. Unfortunately, a lot of those boxes that are optimal are not. They're not necessarily attractive. They might be difficult to work with. Maybe they don't stack well on supermarket shelves. So there's other things that come into consideration too. But what you see here is a model being, well, you can see a data set, right, where we have the square inches of cardboard used to build a particular cereal box, and then the net weight of the cereal inside the box. And along my x-axis, I've set up the square inches, right, of cardboard. So this is cardboard used, and it's important to keep in mind what the x and y axis represent. So the way this was set up, the x-axis is the cardboard used, and the y-axis is the net weight of the cereal. And you can see I've plotted these points. Now, once I plot the points, right, I can move around and I can talk about the general shape, the direction, if there's any outliers for this data set. When I look at this, to me, it looks like it's slightly curving upwards. So I could say maybe there's a curve here. It's curving upwards. The direction is positive. It's clear that as I increase the square inches of cardboard, right, the net weight is also going up. So it's a positive relationship. As one variable x increases, the other one's going up. And I don't see anything that I would consider an outlier here, right? Most of these look like they're in the same place. So let's kind of review some things I know that you did in maybe way back in 7th grade or 6th grade even, but the general shape, the direction, and if there are outliers in the set. If I was to draw a line of best fit, it might look something like this, right? And you can see the way I've drawn this, it's nice because there's 2 points, like point B and point E, look like they are on the data set. There's no reason why I have to do that. If I felt like this would be better, I could go with something along here. It is nice when you're doing it just for convenience right now. If you try to draw it in such a way so that you can see a couple decent points. So where I've landed this one now is I could see this particular data point here, right? It looks to me like when x is 450, y is 900, and down here it looks like when x is 50, right, the net weight would be 0. So so I don't know that that's great. I think it's kind of it. I should mention the fact that it's okay that this seems kind of goofy, that if the box had used 0 square inches of cardboard, you could have negative cereal in it, in negative 100. So though I don't think the y-intercept particularly makes sense in this context, but you get the general idea that there's nothing magical right now about how we pick the values that are going to determine our line of best fit. The point is that we come up with a line of best fit. If I was to go back and say, well, let's consider these 2 points, E and B, I could use those points, right, to come up with an equation that modeled this data. I would do so by just using the fact that I've got 2 different x, y values, right? Here's an x and here's the y that goes with it. Here's another x and here's the y that goes with that. And I could come up with the model. So that's what I want us to do next. I want us to just, actually, no, I'm running out of time. We're not going to have time to do that. Well, now wait a minute. I say we don't have enough time, but then I remind myself, hey, I'm actually not having you do one of these on your own. So this is what I want us to do. So let's go ahead and build a model on those 2 points. And we're going to start by finding the slope that goes through those 2 points. And some of us are still writing this reciprocal, right? We're getting delta x over delta y. It's important we remember slope is how much y changes divided by how much x changes. So visually here, right, because I'm using the 2 points I've highlighted, my change in y is this line, and my change in x would be this line. So those are the two things I'm trying to find. I'm figuring out the delta y and the delta x, and that ratio is the slope for this line that I'm claiming is the line that's fitting this data. So for change in y, I'll take and write 680 minus 198. So do get this in your notes, this example, finding the line of best fit, and then we're going to calculate at least one residual. So 680 over 198, and then down below we're going to have 357 is that x that went with the 680, and we're going to subtract 150 from that. So let me grab a calculator here. So I've got 680 minus 198. So my numerator is 482, and I'm going to divide that by 357 minus 150. That's 207. So 680 minus 198 over 357 minus 150. So if I want to calculate the slope, I'm just going to go up and grab the rise, enter, and I'm going to divide it by, go grab the run, enter. So it's that fraction, and let's go ahead and make that a decimal. So we're going to say that our slope, slope, is approximately, let's put approximately for this model, 2.33. 2.33 what? Okay, the units were inches of cardboard. So cardboard inches squared per grams of cereal, right? So just so I'm aware what that means, it means every single time I increase the square inches of cardboard by 1, my model says I can put another 2.33 grams of cereal in the box. So that's 2.33 grams of cereal per square inch of cardboard. So I still don't know the y-intercept. I can see the y-intercept's negative and it's past 100 here. So let's go ahead and calculate the y-intercept. So we'll do the same thing. We'll go ahead and write y equals mx plus b. I'll use point B. Yeah, I'll use point B, which is this one, to figure out b lowercase b, my y-intercept parameter. So I'm going to go ahead and write y, which is 198, equals m, which is about 2.33, times x, which is 150, and then plus b. So a lot of times when I'm doing calculations like this, I don't like, I have a more accurate version of the slope on my calculator screen. So a lot of times I'll actually use that. So in order to solve this, I'm going to take and I'm going to multiply these two, and then I'm going to subtract that from both sides. So I'm going to take 150, and I'm going to not subtract, I'm going to multiply it by all those digits that I have stored up above. So this is going to be a little bit different if you use 2.33, but I'm going to grab that. Okay, so that's what I get when I multiply those two. And now I need to subtract it from both sides. So I'm going to take 198, and I'm going to subtract that number from it right there. And when I do that, I get that my y-intercept, yeah, that's pretty much what I thought, is about negative 151.28 if I'm rounding. That's what B is. Okay, so now I have this model, right? Let's write down what the model is. The model is y equals 2.33 times x minus 151.28. Okay, this model is used to make a prediction. This model takes an x value. It takes an x value like 400, and it predicts how much cereal I would be able to fit in the box. So it would literally, the model will give me the value that's on that line when I plug it in. So the model is made to use predictions. Now, the actual value are the values that are stored in my data set. So what we're going to do is we're going to calculate the residual for point F, right? So this is where we're going to end today. There is a residual right here. Point F has a residual, and we can see that it's positive because it's up above the line. So we're going to calculate what that residual is for that particular data point. And to do that, I just remind myself that the residual is equal to the actual value, right? The value stored in our data set minus what's predicted. So for point F, for this point, it has an X value, right? It has an X value of 471. That's the X value that I'm going to use to get the prediction for my model. And it also has a Y value of 1020. That's what the actual value is. So I can say, okay, so the residual is the actual, which is 1020. That's the value stored. That's the actual value in the data set minus what my model predicts. So I got to calculate what the model predicts, and I'm going to calculate that using this equation. So I'm going to put this number in for X, and then this model is going to give me the prediction. So the model says, okay, you're going to take 2.33, multiply it by your X, and then subtract the 151.28. So let me clear this screen. I'm going to take 2.33. I'm going to subtract, no, I'm going to multiply. I'm going to multiply by the 471. Got it. 2.33 times 471. And then I'm going to subtract 151.28. So my model predicts that I should get, it predicts when X is 471 that Y should be 946.15. So you can see that's lower than the value that was stored in my data set. So my residual is this actual 1020, that's the one number recorded in the data set, minus what's predicted, which is 946.15. So it's a subtraction problem to get what the residuals is. It's 1020 minus 946.15. There it is. The residual is 73.85. Great. And it is a positive number too. And I'm going to see that every single time I calculate the residual for a point that's above the model. I'm going to see that it's positive. And if it's below the model, I'm going to see that it's negative. All right, so I guess I'm ending 10 minutes early since I'm not going to have you do anything else other than those couple of note items. So we can say we're done with 412 in terms of talking about residuals, what they are, and how we calculate them. And you can move on to the review preview. This is Mr. Roberts, as always. I appreciate you, and I hope that you have a great day. Talk to you soon.